In the last video, we learned how to tell whenever JAX is compiling, transferring, or really executing. Now, let's send a training job to the GPU.
A clean JAX training step is a pure function. Parameters optimize a step and a batch goes in. New parameters, new optimize a step, and metrics come out.
Before coding the model, be sure you prepare your data properly. In our notebook example, we get checked, normalized, reshaped, batched to a fixed size, and placed on the GPU. And again, fixed batches keep the compile step reusable.
The model we decided to start with is a small MLP. We did not pick it to envision benchmarks and train a frontier model. The goal here is to see logits, cross-entropy, accuracy, gradients, and updates without getting overwhelmed by architectural details.
First, we do one update by hand, so the compiled version is transparent to you in the notebook. The JAX value and grad returns the loss and a gradient tree. The gradient tree has the same structure as the parameter tree.
Then Optex AdamW gives us the practical optimizer pass. Same idea. Compute gradients, update optimizer state, apply updates. JAX JIT stages the whole step for the GPU.
But here is when the code can quietly slow a loop down. Remember to not convert metrics to Python every step. Log occasionally, block intentionally, and keep the loop on the device.
After training, evaluate on fixed test batches. Inspect predictions and check the confusion matrix. A useful loop tells you what the model is doing and not simply follows the loss curve.
Now, let's move from our simple MLP to one of the most common workloads of today's models, the attention one. The attention is 4 moves: score Q against K, scale, softmax, and then mix B. Of course, implementation matters. Bear in mind that the naive attention mechanisms, like the one as shown in the notebook, can lead inefficient behaviors on GPUs.
In the notebook, the naive pass materializes the full attention matrix. That matrix grows with sequence length squared. So the sequence length sweep is where we see dramatic changes on the latency curve.
The default practical move is JAX NN dot product attention. Let JAX and XLA fuse the operations. On supported NVIDIA GPUs, implementation equal QDNN can use fuse QDNN attention with BF16 or FP16 inputs.
Decoder models need causal attention. Each token can only look backward. For inference, MHA, GQA, and MQA all produce the same output shape, but have different KV cache costs. That causal attention is exactly what we plug into the transformer next.